この会場はですね、次のセッションは libuv の話をします。libuv fats a unicorn velociraptor。これがユニコーンベロスラプターなんですね。なんかlibuv っていうのは Node.js の中で使われている、非同期 IO を処理するためのライブラリになっています。で例えば Node.js ってシングルプロセスで、イベント IO モデルですって言われてるんですけど、それは何が支えているかというと、libuv っていうのが支えています。で、スピーカーはコリンさんですね。コリンさんは、libuv のメンテナンスをしながら、libuv の新しいアップグレードがあると Node.js にNode.js コアにコミットしたりとか、そういうことをやっている人です。じゃあ、皆さんまた拍手で。はい。
Thanks for coming to my talk, everybody. So, the purpose of this talk is to try to answer the question of what is a unicorn velociraptor. So, if you were to ask Google, this is what Google thinks a unicorn velociraptor is. I think the second row is probably my favorite, with the Chicago Bears football player riding the dinosaur, the cat and the unicorn. But what we're really here to talk about is the one in the top left corner, which is the logo for the libuv project. So, libuv is a platform abstraction library that's used by Node.js. It's mostly focused on asynchronous I/O. It is written in just very basic vanilla C, so it's very portable across a lot of platforms. And it allows you to kind of access a lot of lower level things that JavaScript as a language doesn't really provide APIs for. So JavaScript has kind of limited access to the file system and other things like that. And that's kind of what libuv gives to Node.js. It was developed primarily for and used mostly by Node.js, but it has several other large consumers such as CMake, Julia Lang, Neovin, and some other ones that I'm probably forgetting right now. And the very first thing I want to talk about is kind of the different platforms that are supported by libuv. So if you notice at the bottom of the slide, the little cartoon head is Saul. He's another one of the libuv maintainers, and he has some very good one-line quotes that I didn't want to not attribute to him. So occasionally throughout the presentation, he'll pop up with some words of wisdom. And he says on this slide, we write the if-defs so you don't have to. Basically, if you look through the Node.js source code, there's not really a ton of if-def logic. A lot of that has been pushed down into libuv land. And if you look through the libuv code, there's actually quite a lot of if-defs. We actually have an entirely different implementation for Linux and macOS than for Windows. We have different tiered platform support across all these different platforms. So tier 1 is going to be your Linux, macOS, Windows, and FreeBSD. Tier 1 basically means that every single patch that's submitted to the project is run on our CI. And if any patch were to break the CI, then we would have to either modify it or reject the pull request. And then below that, we have our tier 2 support, which is officially supported, but not necessarily tested with the CI. I think we actually need to go back and update our tier system because SmartOS, AIX, and ZOS are all run in the CI. So I think they should actually be tier 1 platforms. And then the other tier 2 platform is going to be Muscle Linux. Then when you drop down to tier 3, this is basically community maintained. So a lot of platforms out there, I guess Android is probably the big one. We don't test it in the CI. We have no way of verifying if things actually work or not. But if you care about it and want to submit pull requests, we're happy to at least look at them. Can't make any promises about if they'll get accepted, and if they may break from time to time. You're kind of on the hook to keep up maintenance. So this is kind of a list of some of the things that libuv provides, and I'll kind of translate into what they represent in Node. So everyone is pretty familiar with the event loop. If you've ever used Node's net module or dgram module, then you're using libuv TCP and UDP sockets. We also have DNS resolution. So Node.js has two different ways to do DNS resolution. I'll come back to that a little bit later. libuv also provides file system operations and file watching. So all the things that happen with the FS module go down through libuv into a thread pool. libuv also provides child processes, threads, synchronization primitives, and then we have a high-resolution clock. So date.now in JavaScript is not known for being super accurate. So if you were to use process. I think it's HR time, that's going to give you a high-resolution clock that comes from libuv. So at a very high level, this is what the architecture of libuv is. I kind of like to break this diagram down into two rows. So the top row is more of the user-facing APIs. So like the purple things, TCP, UDP, those are different sockets and I/O systems. Then over to the right, we have file I/O, DNS operations, and then user code. You can actually submit your own user code to libuv and it will run it for you inside of the thread pool. The bottom half of the picture is more of the internal guts of libuv. So for example, we have UV-IO type, which is going to handle different types of I/O operations. And then depending on what platform you're running on, we'll actually use a different asynchronous I/O primitive. So for example, if you're on Linux, we're going to use epoll. Mac and FreeBSD are going to use KQ, and then SmartOS and SunOS will actually use event ports. Windows is going to use IOCP. Then the red rectangle down in the bottom right corner of the picture is the thread pool. This is a way to kind of keep the main JavaScript thread unblocked, and you can actually submit different tasks to a pool of thread workers or worker threads that will perform some type of operation and then give the result back to the user. It's a way of not blocking Node's event loop. So one of the important concepts of libuv is something called a handle. It's basically a representation of some long-lived resource. So whether that's a socket, TTY, timers, child processes, things of that nature. We also have different types of handles that are basically hooks into different periods through the event loop. I'll come back to that in a couple of slides in more detail. If you've ever used Node's unofficial process._get active handles, it will actually show you all of the active handles inside of libuv. These are what keep your Node process alive. So as soon as the process runs out of active handles, or you perform an unref operation, which basically tells the event loop that it can pretty much ignore those handles, that's when your Node.js application will exit. So along with handles, requests are, I like to think of requests as functions or methods, where I like to think of handles more as objects, if you want like an object-oriented kind of comparison. And the reason that requests can be compared to functions or methods is because sometimes they act on a handle and other times they just kind of are their own thing. So examples of these are going to be socket connections, file I/O, DNS lookups, and then any user-defined work that I previously mentioned. Like I said, some of these operate on handles, but not all of them do. And like handles, these will also keep your event loop open and keep your Node application from exiting. So if you were to, for example, do a DNS lookup, and that were the only thing inside of your Node application, your application won't exit until the DNS lookup returns, because that request is holding the event loop open. So the next thing is the thread pool. Like I said before, this is the way to move computations off of the main thread. JavaScript has one thread of execution, so if you block that, everything blocks. So basically what happens is you submit some type of work into the thread pool, and then once it comes back, it'll actually trigger a callback, and then execution will continue in JavaScript. The size of the thread pool is controlled by the UV thread pool size environment variable. If you set that, by default is set to 4, so there's 4 libuv workers. If you set that to a different value, when you start up your application, you can kind of more finely tune the size of the thread pool. In general, if you don't have a reason to mess with it, I would recommend not changing the default value. But if, for example, you have a lot of file system operations and you're finding that is actually slowing down your application, you can actually bump up the number of worker threads, and that should help performance. One common misconception is that everything that goes through libuv is done in the thread pool. That is false. The only things in libuv that use the thread pool are the file system operations, get address info, get name info, so your DNS operations, and then any kind of custom user-defined work that's passed in. So this is a high-level view of what the event loop looks like. If you actually go and look at the C code, it's not all that much different from this. So at the very top of the diagram, we update the loop time. This is libuv has a concept of what the current time is. We update this once per iteration because it's a somewhat expensive operation, so we don't want to keep updating the time as we go through. After we update the loop time, we check is the loop alive. That just basically checks if there are active handles and requests. If there are none, then the process will exit. If there are still work to be processed, then we drop down below. Basically, we start by running do timers. So in Node.js, if you do set interval or set timeout, eventually those timers are going to elapse, and then these libuv timers will actually be triggered. Then we'll call any pending callbacks. So if you've submitted operations to the thread pool or anything like that, and they've completed, you have a pending callback that needs to execute, we'll execute at that point. Then we run idle handles. The name for idle handles is not very good. They run on every iteration of the event loop. It has nothing to do with whether or not things are idle. But this is a chance to kind of, if you wanted to attach an idle handle to the event loop, you can kind of inspect the state of things here. Then we want to run what's called a prepare handle. Prepare handles are basically an indication that we are about to begin polling for I/O. The next step is we actually do poll for I/O. If you remember from a few slides ago, the high-level architecture with the KQ and IOCP and event ports, this is where we poll for I/O using those mechanisms. After we're done polling for I/O, we run check handles. Check handles are kind of the inverse to prepare handles. So prepare runs before polling, check handles run after polling. And then finally, if any close callbacks are still pending, like a resource has been closed down and there's a callback, we run that, then loop back up to the top. This is kind of the extent that I'm going to cover the event loop in this talk. If you see Burt Belder's Node Interactive 2016 keynote on the event loop, it has a lot of really good information in it. One other thing to note is that promises do not use this event loop. They use the microtask queue inside of V8 and are kind of their own special snowflake. So this is what Node.js looks like in the context of libuv and all of its dependencies. So in this diagram, everything in yellow is JavaScript code. Everything in purple is C++ code. The gray stuff at the bottom is boring operating systems code. I've included some diagrams in this bottom row of different Node.js dependencies. These are things that are compiled into the Node.js binary. So I started with libuv on the left, and then kind of everything else off to the side. This talk is about libuv, but in reality it would probably be V8 and then everything else. So V8 is going to be the JavaScript engine that executes all the JavaScript in your application. C-Aries is a library for doing DNS lookups. So earlier I said that Node.js had two ways of doing DNS lookups. One is through libuv, which uses your system resolver. So for example, if you were to run a command like ping, Ping uses your system resolver to kind of determine DNS operations. libuv would give you the same results. C-Aries is a separate library. It stands for C, Asynchronous Resolution Resolver. And funny thing about DNS operations in libuv is that for a long time they could actually conflict with file system work that was being sent to the recently, Anna, who's in the back of the room, submitted a pull request to libuv to make it so that these different resources can't contend with each other. So for example, if you run, in the past, if you ran a ton of DNS operations, you would see that your file system operations could actually be starved because there was only so many thread pool workers and they were waiting for DNS results to come out. Now we have a kind of partition that the DNS lookups can't take up more than a certain percentage of the thread pool workers, and so that starvation isn't really an issue anymore. And then finally, OpenSSL is what Node uses for all its crypto and things like that. So Saul is back at the bottom of the slide to talk about the onion architecture. The more layers that you peel away, the more you cry. And that's a pretty accurate description of some of the data structures inside of Node.js. So if you've used net.socket, it has a it has a streaming API. It's pretty easy to work with. But then it has, I think they've recently been removed or hidden. But there was an underscore handle property which points to this C++ object, which is a TCP wrap. And then the TCP wrap itself has its own handle, which points to a UV TCP type inside of libuv. And then libuv wraps whatever the actual operating system construct is, whatever the socket is on that platform. So I wanted to talk about testing a little bit. libuv has over 300 tests. They're written in C, and they're kind of a pain to write new ones. But they do the job. We don't have a ton of regressions. But we would run into this case where we would make a new release of libuv, and then all the tests were passing. Then we would go to update it in Node.js, and all of a sudden some condition in the Node test suite that we weren't testing in libuv would trigger some failures. So we would actually have to go back and cut a new release. An example of this on this slide is earlier this year we cut 119.0, and they had a regression in Node.js. It never made it into an actual release, but there are some people out there who actually, as soon as a new version of libuv is released, they actually build their own Node.js. So this kind of created a non-ideal situation for them. So we got everything patched up in 119.1, got it out the door, and kind of moved on with life. But we kept bumping into this problem over the months and years. And so we started thinking, what if there was a way that we could actually test libuv inside of Node to make sure that none of these regressions were popping up, and we could cut down on these extra releases that we were making. So we did just that. The Node.js build working group was kind enough to create a job for us where we could test a libuv branch inside of Node.js's master branch to make sure that the tests were running properly. And this actually gave us access to a lot more tests. So Node has over 2,300 tests that are run on each CI run. They're JavaScript tests, so they're much easier to add new ones, modify, things like that. And since this has happened, we haven't had that issue that I talked about. Not to say that there have never been regressions, but we haven't had the issue where we've had to go back and keep creating new releases because of some unforeseen test failure. So then the next thing I wanted to show you is I wanted to trace some JavaScript code all the way down into the libuv thread pool. What this slide shows is 3 different ways of performing a copyFile operation in Node. The first one is a synchronous operation that blocks the event loop. The second one is using async await and promises. That's in the FS module as an experimental feature. If you didn't know about it, I would suggest checking it out. And then the final one is just the old callback-based copyFile mechanism. So the code shown here is the promises-based code, because it is a little bit cleaner. It fits nicely on the slide where the other ones may not. There are similar functions inside of Node for callback and synchronous calls. Basically, all we're going to do is take the source and the destination, do some validation on them, so make sure that they're valid paths and things like that. Then we're going to look at the flags. So there are different flags that can be passed to the copy operation, like copy on the right side, fail if the file already exists, things of that nature. And the or 0 is kind of a V8 trick to force the value to be coerced into a 32-bit signed or a 32-bit unsigned signed integer. And then after we have the flags, we're going to call down into the binding layer, which was the C++ purple layer in the diagram from a few slides ago. So these are what the different calls into the binding layer look like. We're calling the same function, binding.copyFile, but we're passing different arguments into it. So you'll notice all three of them, we pass the source and the destination of the flags. And then we either pass undefined in a context object, or a k-use promises symbol, which will kind of let the binding layer know that we're doing something with promises, or we're going to pass in this request object, which is just a C++ object that the binding layer knows indicates a callback-based call. So I guess bear with me a little bit. This is a lot of code on one slide. It's the most code that I have on any of the slides. This is what the binding layer's copy file looks like. We're going to do some, you'll see the like check GE and check not null calls. This is kind of some last ditch validation where if the condition isn't met, the process will just abort. And the reason we do that is kind of to provide one last layer of validation before we call into libuv. And if things crash, we're kind of okay with that because it's expected that all the validation has been done in the JavaScript layer already, and that any users who are using the binding layer directly on their own are kind of left to their own devices. So after we do a little bit of input validation, this function getRecWrap is what we use to determine if we're doing an asynchronous or a synchronous libuv operation. So if the recwrap that's returned by that function is not equal to null, then we're doing an asynchronous operation, and then otherwise we're doing synchronous. I'm not going to go into what all the different arguments mean because there's a lot of them and they're not really relevant to this talk. But you will see that you'll see copy file, the source is passed, destination, the flags, things of that nature. So from that point in the binding layer, we drop down into libuv. This is kind of the Unix version of uvfs copy file. Init copy file is a macro that's going to be expanded to basically initialize a thread pool request, object. The copy file tells it what kind of operation it's going to be performing. Next, we do some flag validation. So if you pass in an input flag that libuv doesn't understand, it'll return with uv, e, and val. Path2 is another macro that's going to actually copy the path and new path arguments onto that same request object. Then rec flags equals flags is just going to copy the flags integer over. And then finally we have the post macro, which is actually going to go and either execute this if it's a synchronous operation or submit it to the thread pool if it's an asynchronous operation. So this is the post macro from the previous slide expanded. It's going to check if callback is not equal to null. So in that case, we know we're dealing with an asynchronous operation. We're going to do some UV rec register, which basically increments a counter. It tells the event loop that it's tracking one more piece of work. And then we do UV work submit. So this is where the thing actually gets sent off to the thread pool. UV_FS work is basically a large switch case for all the different operations that are supported. So in this case, that UVFS work will do a file copy operation. And then UVFSDone is the C code callback function that's going to then be triggered after the work is completed and go back to the binding layer and back up to JavaScript finally. The else branch here is if it's a synchronous operation. So you'll see we're actually calling UVFS work directly and then just returning whatever the result is. So on macOS, we have a copyFile function that's provided by the operating system. So we just use that directly. So basically, we just validate some of the flags and then pass off the work to macOS to do the actual copy. There's actually a Linux implementation that's based on send file, and if the send file isn't available, then it's going to manually copy bytes. It's a lot larger and uglier, and obviously won't fit on a slide, but you can feel free to go look at it if you want. Similarly, this is the Windows operation. Windows also provides this copyFile W function. It's pretty much the same as the macOS version. It does some input validation and then passes off the work to Windows to actually copy the file. So the last thing I want to talk about is libuv 2.0. This is something that we need to get done. libuv 1 was released in 2014, so it's now about 4 years old. It's largely been API and ABI stable, save for some accidental breakages that we've gone back and tried to fix. We want to do some things like basic cleanup and some new features that involve breaking changes, so they couldn't be released in the 1.0 branch. The problem is libuv has a fairly small team of maintainers compared to the army of maintainers that Node.js has. So we still have to support v1.x until April of 2021 because that's when Node 10 will be end of life and libuv1 is inside of Node 10. But this is something, like I said, we need to get done. There's actually not a ton of really notable stuff in it. Normal breaking changes, so we tweak ABI and API in some places. Some functions to work with CPU affinity. These can actually mostly be backported to v1.x. There's, I think, one function that actually does break. We have a UV password type that does a password file entry lookup. We added one field to that, which will break ABI, but that will basically let you call nodes os.getUserInfo, and then it returns whatever the password entry is for the current user. We added this macos field, which is going to be like the human name as opposed to the username, the machine username. And then we added some more functions for working with file times, basically things that will let you set the birth time of files, but it involved breaking ABI, so it got pushed off to libuv 2. And that is everything that I have for today. Thank you.
ありがとうございました。ちょっと時間があと5分ぐらいないかな。Until the next time. Okay. Thank you so much. Very much. So next one, there's a